questions. I'm going to definitely keep an eye out for new folks joining. Anybody want me to go over something from last week? Please, right? Let me know. I might just make one up myself here in a second, then otherwise, just a couple questions I saw about certain kinds of problems. And 9. I'm looking at my class list. Hi, Christina, you made it, that's good. Well, all right, so we're going, here we go. Get to work, Steve. And so first of all, of course, notice, I hope you're all aware, yeah, right? All that last week homework stuff is due by midnight tonight. Most of you are in good shape as far as that goes. A couple of you that joined really late in the week last week, please send me another message or email and let's talk about it. You know, maybe I can give you a little extra time to catch up, but you know, you don't want to fall too far behind. The other thing is the hand-in homework that, you know, print out that page and or do it on your own paper and then scan it into me. And I've tried to reply to those of you who submitted or basically asked a question, did you get it? And I haven't started grading them yet. At this point, I'll probably wait until tomorrow, until hopefully you all turn them in, and then I'll sit down and spend my afternoon or something like that grading them, or maybe late tonight. I'll get started later tonight. I've got chores to do around the house. You know how that goes. That's got stuff to do myself today. Anyway, okay, our topics. I'm going to make up a couple evaluation problems that some of you asked about, just to emphasize a couple points there. So how about one like this? So here's one of those expressions that has 3 terms in it. And there's x's in a couple different places. And I purposely put in some negative signs for us to wrestle with. And then we're given a value for x to put in and evaluate it. What do you get if x is this number? So I'm going to make up a number, say x is -4. What do you get if x is a -4? And in particular, I'm emphasizing a negative there because that's, you know, well, kind of where you can get messed up if you don't deal with it correctly. So everywhere there's an x, I'm going to put in that -4. Because there's a negative sign, just from the start, you should think I'm going to put that in parentheses wherever I put it in, so that that negative is enclosed. It's part of x. So just substituting. Here it comes. There's the -4. The negative is inside, and it's going to be part of what's getting squared. That's important here. -2 times this -4, and then the 5. So that was just a substitution step. Now I'm following order of operations rules to simplify it. Well, that's not really a grouping other than holding that negative sign there. So the next level in our hierarchy is look for anything with exponents. Yes, there's an exponent. That exponent is only attached to that -4, not to the 3 also. So that's going to end up being -3 times, now that's -4 times -4 turns positive, 16. I just want to do a real quick breakout on the side. What if I had 3 times, even without parentheses, 3 times 5 squared? As get my multiplication dots bigger again, right? What if you had seen that expression? Again, the square is only attached to the closest number or expression. It's not 15 squared, it's just 5 squared and then times a 3 on the outside. So anyway, that's almost helped by the parentheses in this case. Kind of helps to say it's only the -4. But then going on, I can keep working across. I actually did the squaring. I could just rewrite that because I did the squaring, but the next thing is going to be multiplying. -2 times -4, negative, +8, plus the 5. At the next step, we are still multiplying. 3 times 16, 48, negative 48. Negative 48 plus 8 plus 5. So we took care of the squaring, all the multiplying, and now we're down to addition and subtraction. Take them in order from left to right. It's really like saying negative 48 plus 8 plus 5. Negative 48, if I add an 8, I'm still pretty negative. Negative 40. And now negative 40 plus a 5, a little less negative, negative 35. So there was an example. Square the negative, plug it in every spot there was an X, and go from there. Just going to do one more like that. Any questions or issues at this point? And I'll just say again.
Is there a good trick to remember, like the way, like when you're doing two negatives and it turns into a positive? Like I have a really hard time remembering all that.
Okay, sorry I missed that. Who was that? Who was
that? Was Emma.
Hi Emma. All right. Right. I saw. You know, you had that message to me earlier. Adding. Well, so this is. You could say this is 2 times negative 4 would be negative 8, and then we're subtracting a negative. So it's still minus times a minus, we get a positive. Remember that rule if if this is a negative 3 minus a 4. All right, it started at negative 3 and I minused some more. I went more negative. Turns out to be negative 7. I can always think of this as, remember, problems ask you to rewrite it as the addition or sum of signed numbers. So this is like negative 3 plus a negative 4. And here I use the parentheses because I didn't want plus and minus right next to each other. So yes, I have a negative 3. I'm on the left of the number line. And I'm going to add some more negative, go even further negative. So that's how we deal with minus and more minus, you might say. All right. If I have a number and I subtract a negative, this is taking away a debt, right? Taking away a negative. So the result is that I'm actually adding it. If you see minus a minus, it's the same as adding. So this is equivalent to 5 plus 8. And I would get my positive 13. So that's the kind of things to watch out for when you're adding or subtracting with negatives. Now, for multiplying, we tried to make make it look like nice rules. Sasha helped with a posted picture. But if I have 2 negative numbers multiplied together, it's like the opposite of times an opposite. It returns positive. Minus times minus is positive. If I have a negative times a positive, it's still a negative. I have negative 3 times is 4, or 3 times a negative 4. I have lots of negative. 4 times negative 3 means lots of negative. Negative 12. Opposite signs results in a negative. Same signs results in a positive. Keep practicing, send me questions. Even the ones saying mom, or even if you finished it, you can go back and try another problem. If you see that near the bottom, maybe it's only if you get it wrong, but maybe you can even reset and try it again. Or just make up your own. And if you think you get stuck, you just message me and ask me, would this be the right way to do it? And I'm pretty good about getting back to you within a day if you'll message me. Okay, for now, we'll keep going. I know that didn't just completely magically clear it up. You have to kind of practice and get comfortable with it if you're having trouble occasionally. I was going to do the similar one here. What if I had a fraction? And still I'll make it a negative. What if x is supposed to be a fraction? Now the last one I just did, what might have been something you ran into section 1.4, where we were dealing with integers, positive and negative numbers. 1.5, 1.6, we started including fractions. So we might evaluate the same expression with a fraction. Same thing, start by plugging it in. Parentheses because it's negative. Otherwise, I might have said times a 3/4, but maybe just because it's fractions, I might have put parentheses around it anyway, just kind of make it look better. But anyway, negative 3/4, that fraction by itself is going to get squared, not including the outside, negative 3. And there it is again for that other x, and there's the 5. So here we're going to end up with some fractions, and then we're going to have to add or subtract fractions, make sure we have common denominators, things like that eventually here. So again, no real grouping, but I need to square. I need to square that fraction. Now it is negative times negative, so that'll become a positive number. It's going to be negative 3 times some positive number. 3/4 times 3/4, squaring it. Multiplying fractions. Multiply the top numbers together, multiply the bottom numbers together. That's supposed to be the easy one, you know, we don't have to worry about common denominators when multiplying. I know I don't usually like to say the word easy, I understand, but I say it that way sometimes, you know. And so that's 9/16. 3 times 3, 4 times 4 is 9/16. Now, I'll just keep going, not do too many things. That was just the squaring step. All right, the squaring. Now I'm just going to multiply here and multiply here. All right, got rid of the exponent onto multiplication. So nothing to cancel, huh, shucks. But 3 times 9, negative 27/16. This could be, now I could do 2 times this fraction and then still have a minus sign in front, but this really can be thought of as negative 2 times negative 3/4. Minus times minus, we're going to get plus 6/4. And finally, plus 5. Now, yes, I could have, you know, thought of that as 2/1, done a simplifying. Maybe I was thinking ahead. I'm going to have to actually get a common denominator of 16. I'm going to have to make that bigger anyway. But so I just did the multiplying. And here's what I have. I could reduce that fraction, but actually, now that I'm adding or subtracting, I need to get a common denominator, same size pieces to push together. All right? It's going to be a 16 because 16 is a multiple of 4. That's nice. Well, that kind of always works out that way because I used 4 to get the 16, right? Well, so how do I turn, I'm gonna leave this one alone. How do I turn this into 16? I'm gonna multiply by 4, which means I have to multiply the top by 4 to make it an equivalent fraction. Like both things got proportionally bigger. 24/16. Now that's a 5, an integer, whole number. But think of it like a fraction over 1. I still have to make it 16 on the bottom. All right. So to do that, I'm going to multiply the bottom by 16, the denominator. I have to multiply the top by 16. Again, to make it an equivalent fraction. Just made them all bigger by the same multiple. All right, plus 5 times 16, 80. All right, now I've got all the same size pieces and I get to start adding and subtracting again in order from left to right. They're all going to end up being a certain number of 16ths. How many 16ths do I end up with? Minus 27 plus 24. I'm still at minus 3, right? Minus 3/16 plus another 80. And I won't go any lower on my board. I think I'm running out of space. So I'm just going to cheat and go over here for a second. Negative 3 plus positive 80, positive 77. So I end up with 77/16. Now that's 7 times 11. So those are 2 prime numbers. No common factors. I can't simplify to lowest terms any further. So that would be my final answer. So again, kind of emphasis here. Watch out, wrapping up your negative signs. Squaring a fraction is squaring the top and the bottom. You know, two of those multiplied together. Negative times negative turns positive. Things to watch out for when evaluating this kind of expression. And that's kind of what I had in mind to back up and review a little. Anybody else? And again, I can remind myself to say, if you're trying to write everything down, copy, you know, always slow me down or stop me before I erase if you need me to wait for you. You okay with that? Can I erase? Here I go. Or not. I mean, stop me if you need to, right? Okay. So I'm going to go on, start our next sections today, but I want to just talk about our schedule, right? We did the first week. Hopefully you're getting comfortable with your time management and figuring out when I can do my homework without the kids or, you know, with other, you know, fitting it in. I find a nice place to work. I'm getting it done on time, and hopefully you're not waiting for Sunday night to get it all done. Little by little, right? We did new things for many of us, positive numbers, negative numbers, and then we mix in the fractions. Oh, I've done some fractions before, but I never like it. You know, well, that's week one. Now we're all experts. Haha, I know. We're gonna keep climbing, all right? If you look at our schedule, we have like 3 sections, really like 4 pieces to get through this week. And right now on my schedule, I have the test next Monday. I'm already thinking maybe I can bump it to Tuesday. I can't promise yet, but I'm really leaning that way, just so we could come back on Monday and review. I know that's usually better. But you can't let down, right? You got to keep climbing, climb through the term. You got 11 weeks of climbing. So just encouraging you to keep up with your own time and stuff, all right? So you may notice we skip 1.7. 1.7 is doing all our arithmetic operations with decimals. I'm going to just address a couple basic things. Maybe the nice thing for you guys is, well, I get to use my calculator for everything, and I know I can plug decimals into my calculator and it'll tell me the answer. But we should understand some basic things, all right? So here's a number in decimal notation. Decimals really are a notational shortcut for saying these are parts of tens or hundredths. You know, they're fractions with multiples of 10 on the bottom, or powers of 10, 10, 100, 1,000. This represents a fraction with some multiple of 10 on the bottom of that fraction. So place value is the first concept. Hopefully we were okay over here, ones, tens, hundreds, and so on. We kind of go opposite when we're going to the right in our decimal places. These are tenths, so that really represents 5/10. Next column are hundredths, so these are 6/100. If I want to look at them together, I actually kind of use the denominator for the furthest right, and I could say that together those are 56/100. So there's sort of the fraction equivalent of that decimal. Understanding place value, thousands, 10,000s, and so on as you get further to the right. All right, and now add and subtract. The big deal is line up the decimal points, or in a sense, the place values. If I have, and I want to add, say, I'm going to add 6.032. To do this correctly, you want to get the place values in the same columns. So the best way to do that is get the decimal point in the same place. So that means the 6 is here, and there's a 0, and a 3, and a 2. And I made that an addition problem. So there's if you're adding them by hand. Line up the place values, line up the decimal. Now I'm ready to add the columns, just like a regular arithmetic addition problem. Notice I purposely put an extra place value in this one. There isn't one up there. You can add as many zeros as you need up to the end of one of these if you want. Doesn't change its value. But now I have something to add the 2 to. That gets me a 12. Here's my arithmetic, carry the 1. That gets me a 2. That's a 9, and that's a 5. So line up the columns. Subtraction would be the same. In fact, let's do that just because there's always that borrowing aspect, or often is the borrowing aspect of the subtraction problem. If I had to subtract those, well, I definitely need something to subtract the 2 from, so I need that 0. Well, now I have 0 minus 2. Really, I'm going to borrow right away. Remember that arithmetic concept here? That makes this a 10, but now I only have 8 left over there. So now I have 10 minus 2, 8 minus 3, 1 minus 0, 3 minus 6, so I need to borrow some more. So 4, and that becomes 13. 13 minus 6, that's a 7, and there's the 4. So subtraction, very similar, just watch out for that borrowing. Again, I know your calculators will help you out with that. Multiplying and dividing. Now, when you're multiplying, you don't have to worry about the place value. But at the end, we have to figure out, well, how many decimal places do I really need in my answer? There's kind of, without trying to get into a technical explanation, there is this rule or shortcut. Your final answer, right, if I'm multiplying, has to have the same number of decimal places as the sum of all of the decimal places in the 2 factors. So here's 2 and a third, so a third decimal place. So there's going to be 3 decimal places in my answer. Now I'm not going to worry about it until I'm all done, just doing my regular arithmetic multiply. 6 times 5 is 30. I need that 0 for the decimal places later. There's the 3 from 30, right? 1 times 6 plus the 3 is a 9. 3 times 6 is 18. All right. Now, just like without the decimal point, I'm going to move over a column, start from the 2. 2 times 5 is 10. That carried a 1. 1 times 2 is 2, plus the 1 is a 3. 2 times 3 is 6. Now, at this point, you always add those, right? 0, 9, 11, carry the 1, 6, 7, 8. There. Now, I got to put my decimal point in. Well, 1, 2, 3 places. Start from the back. 1, 2, 3. That means that decimal point's got to go there. This is 8 and 19/100ths, or 190 thousandths, or 8.19, however you want to say it. And if you're not sure, does that make sense? Well, this is 2 times 3 is 6, and we got the extra stuff, so it's going to be a little more than 6. Oh, yeah, okay, we're in that ballpark. You can help yourself out by doing some estimating like that. One more, a division. Just kind of like a quick going through the stuff. Let's say I have make it look like that old, everybody's other favorite is long division. Well, what if I have this number divided by this number with a decimal point? To avoid the messiness of that decimal, dividing by a decimal, and where is the decimal point going to go, we multiply this by some power of 10 times 10 or times 100 so that it moves the decimal point over. Well, if I'm multiplying that one, I have to multiply that one to make them both equally bigger, proportionally bigger. Now, to move this over, if I multiply it all by 10, it gets 10 times bigger. That moves it over 1 place. If I had 2 decimal places, I'd have to multiply by 100 to move it over 2 places. So I'm going to multiply both these numbers times 10. 10 times 2.5 is 25. 2.5, you're all right with that. And then this one times 10 is going to move that one over. Now I could do the long division. Again, your calculator doesn't care if there's a decimal in both numbers and it'll work out. But if you were trying to do this by hand, you know, you'd want to get it out of there, to get the decimal out of there. I'll do a long division here just because I started, right? 25 doesn't go into 1, so I look at the 17. It doesn't go into the 17, so I look at 175. How many 25s can I get into 175? 4 is 100, another 3, 4, 5, 6, 7. I'm doing a little quickly here, but you can figure that out for yourself, hopefully. And then it's this times that is 175. Oh, look, I made a nice exact number. All right, so that was the first step. When you get here, it's always subtract whatever you multiplied to get. Now I do it again. Well, it doesn't go into, if it goes into that number, means you didn't do enough. It wasn't 7, wouldn't have been big enough, but you bring down the next number. This is actually a good example. This is a little trap here. I brought down the next number. How many 25s in 2? Oh, it still doesn't go in. So that actually means 0. So for that column, I get a 0. For that extra number, there's a 0. Nice thing here, the decimal point just goes right above wherever it started. But now I have to bring down another number. Now, how many 25s? I can get 1. So that was a quick and dirty, as they say, long division. And it had a nice little feature of, yeah, watch out for dealing with, you brought down a number and it's 0, you got to put that 0 in there. You're using your calculators, but we just need to, you're going to run into a decimal problem once in a while. And you need to be able to understand what's going on. Okay, so that's kind of all I wanted to do with decimals. We're going to keep moving. Ready or not? I shouldn't say that. If you're ready, I'm going to keep going. Let me know. Here we go. 1.8. Yeah. I have new markers on order, should be here soon. I hope. The real numbers. Huh? Mathematician language here. The real numbers. Well, just in general, the real numbers are all the numbers we're used to working with in the real environment, you might say, that we can think of it as a size or a debt, you know, in our normal calculations. It means there are some other kinds of numbers that for some reason they're not the real numbers. We don't have to worry about them, but I'll mention them in a minute. We started this term talking about whole numbers. Whole numbers are all these. Started with 0 and on in the positive direction. If we were actually talking about that, I kind of mentioned at the very beginning, the first number sets were probably, you know, based on commerce. You know, how many items are you selling me for how much I have to pay? You know, counting numbers, the natural numbers or the natural counting numbers. If I was asking you to count how many objects you have, you usually start with 1, 2, 3. So that's the natural aspect of it. The natural numbers start with 1. And then I mentioned it was kind of a big deal when they decided, oh, we need to invent a 0 for nothing. So that made the whole, there's my dumb trick, right? The whole numbers have a hole in it, have the 0. We usually draw a little Venn type diagram. Here I'm going to say that's the natural numbers, right? That's set. If I add the 0, it gets a little bigger. And I get the whole numbers, which is just addition of the 0. Then we had their opposites, all the negative values, right? And that became the set of integers. We're getting a little bigger. The integers, right? Set of real numbers, the integers. Well, then we started doing some division and stuff, and we ended up with fractions. Right, fraction numbers in between those nice big whole numbers or their opposites. So our expanded set of numbers includes now fractions. Well, a fraction is referred to as a rational number. That's the set. Rational, and the root word in there is a ratio. A rational number is any number that you can make look like a ratio or a simple fraction. So obviously, you know, 2/3 is a ratio or looks like a fraction. It's a rational number. The number 5. I can make it look like a fraction just by putting it over a 1. All right? And if it's negative, no big deal. It's still a rational number. It just happens to be a negative fraction. So we get this now bigger set of numbers that includes all the things you can make look like a fraction. And those are called the rational numbers. Notice that everything else we've talked about so far, it's like a subset. It's like the Russian dolls or something. One of my kids' favorite playing toys were the barrels that stacked inside of each other. When the grandkids come over now, they just go right to those. They love those. All right, side trip there. Now, rational numbers you can make look like a fraction. Well, how about 1.25? I just got done talking about decimal values. That's really a way to write 25 over 100. All right, this is actually 125 over 100. There's a way to make any terminating, that is, that decimal ends, there's a way to make that number look like a fraction. It's a rational number. If that decimal stops there, which means there are some that don't, then it is a rational number. Okay, so this is the kind of question you'll have to answer, you know, there's the traps here. Could you recognize that could be a fraction? Identify which numbers are rational numbers. If I ask you to write your decimal approximation for 1/3, you know that one? You know, what's roughly, you know, what do you write if you're trying to put 1/3 in your calculator for a decimal? I say approximately equal, there's my wiggly equal sign. 3, 3, 3, and it goes on forever. It's a repeating decimal. It never ends. You can't divide some power of 10 by 3 and ever get an even number. It goes on 3, 3, 3, 3, 3, 3, 3 forever. 2/3 is 6, 6, 6, 6, 6, 6, 6 forever, and so on. 7s have a similar pattern that repeats. Well, that's pretty cumbersome. So we have a shortcut notation. We just say 3 and we put a bar over it. That means that 3 goes on forever, repeats forever, dot, 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 you know, goes on forever. A repeating decimal. So here's the other trap spot. A repeating decimal, whether it's obvious or not, if it's got a repeating part to it, there is some way to make it look like a fraction. You know, I think interest of time right now, if you can accept that concept, you just got to watch for that bar. If it's got that bar on it, it's a rational number. There's a way to make it turn into a fraction. Okay, so if I see 1.56 repeating, 5, 6, 5, 6, 5, 6, 5, 6, 5, 6, 5, 6. Notice here I'm repeating 2 digits. The 2 digits would repeat forever. Sometimes there's 4 or 5 digits and then it starts over. All right. So somehow or other, I can make a fraction, a simple fraction out of this. There is a process. Maybe I get time I can show you, but not a big deal. If you can remember that is a fraction, a rational number. So that expanded our set of numbers. These are all the different kinds of numbers we have worked with so far. What are we getting at? There's more. All right. 25. What number can I square and get 25? Oh, 5, right? What number can I square and get a 9? Oh, 3. What number can I square and get 14? Excuse me, 16. Or what number can I square and get 36? Those numbers I've started with are called perfect squares because they are the result of something times itself. But going backwards, that makes 5 what we call the square root. Of 25. That's a U, right? 5 is the square root of 25. You're okay? I'm going to erase the fractions ratio stuff here. So, of course, there's a symbol, notation for that. What is that's that symbol. It doesn't quite look like a division. That's the square root symbol, that little almost check mark shape, okay? That is notation, kind of like absolute value says how far from 0. This means what number do you square to get what's inside? Well, that number is 5. What number do you square to get what's inside? 9. Is there another number I can square and get 25? How about, right? Negative times negative, still positive 25. So every number actually has a positive and a negative number that you can square to get that positive value. 2 square roots. All right, 2 square roots. So this could be actually be, I could square a 9, negative 9 and get an 81. Well, how do we notate that? Well, we just decide this symbol always means the positive value. And we refer to as the principal or first. Principal square root. There's my abbreviation. Principal square root. If I want the negative square root, I put the minus sign in front. We're basically saying, what's the opposite of the principal one? What's the negative square root of 4? That's a negative 2. Okay, so basically this will always mean what's the positive number that I square to get what's inside. This is telling us what's the negative number I square to get what's inside. And, well, what happens? What number can I square and get 7? That's bigger than 2, smaller than 3. There's no decimal approximation that ever works out exactly even. It would be a decimal that goes on and on and on forever, a non-terminating and non-repeating. There's no pattern. The decimal just kind of keeps going, right? There's no number, no way to express this exactly other than just like that. So there's no fraction. There's no fraction I can make. These I could all make into fractions, right? They were all rational numbers. The square root of 25 is a trick way to say, oh yeah, that's a fraction, because I can write it as 5. Watch out for that one on the questions. Yeah, square root might be a rational number if it simplifies to a fraction. This never simplifies to a fraction, a number I can make into a fraction. So it's not a rational number. What's the difference? What's the opposite of a rational number? We just make up the word irrational. And so our definition is it cannot be written as a simple fraction or as the ratio of integers. So all those numbers so far, we could find a way to write them as fractions. Irrational can't be written as fractions. So now the point of all this is we're going to now do some work with square roots. Your calculator has a square root button on it usually. Sometimes it's the second function on your calculator, that little blue second button or something at the corner. Push the second and then find the square root to access it. You might practice that, you know, find those buttons on your calculator. What's the square root of 25? And it should say 5, okay? But now we have an expanded set, and we know that number there is somewhere between 2 and 3. So it's still in here somewhere on our number line. If you can find a relative position for that number on this real number line, it is a real number. These are still real numbers. we could still talk about that as a relative distance or something like that. So they just happen to be irrational. One of the other most common irrational numbers that we work with that you can't even write like a square root is that one we call pi, and it has its own special symbol. It's the Greek letter P, I think, whatever. It's one of those Greek letters, pi. And approximately, right, 3.14, whoops, I was thinking ahead. I think it's 1415, and then it goes on and on and on, but it doesn't repeat, it doesn't stop, there's no pattern. You know, computers and mathematicians, they've calculated millions of place values for pi, and it never stops or works out evenly. It's definitely an irrational number. You can't write it like a simple fraction. You can get real close. 22 divided by 7, 22 sevenths is about pi. It's real close to pi, but it's not exact. Pi, we'll talk about this more later, but pi is defined as, let's see, the ratio of the circumference of a circle to its diameter. Right? Circumference is how far around, and the diameter is that distance across. How many of those diameters would it take to get all the way around a circle? Well, it takes 3.14 diameters, you know. Here's one diameter, here's two diameters, and here's three diameters, and it doesn't quite make it. 3.1415, blah, 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 blah. So since the Greeks, early times, math times, they wrestled. They didn't like that number. They wanted everything to work out nice. The Greeks were funny that way. They liked everything to be nice, perfect, whole numbers. Anyway, pi is, that's where the definition of pi comes from, that ratio of circumference divided by its diameter for any circle. It's always that number pi. Anyway, it's an irrational number. So here's our expanded set of numbers, of real numbers. These are all real numbers. I mentioned, okay, there must be something else that's not a real number. If you have a square root with a negative, what number can I square and get -4? Well, 2 times 2 is +4. -2 times -2 is +4. Well, -2 and +2, but those aren't the same number. There is no number, no real number I can square and get a negative. I can't multiply times itself and get negative. So this is not a real number. Now, when they invented these terminology, they said, well, let's call this imaginary then. Well, in most of your real life, you will never worry about that. If you're in there actually are some applications like in electronics, charges where they use positives and negatives and their square roots. I couldn't give you a specific example, but there are applications out there. It's kind of like, you know, inner space, something. I think if you end up going to Math 95 and certainly into higher level math courses, you start working with imaginaries, and there are ways to evaluate them and use them in equations and stuff. Don't worry about them. Everything we'll work with is a real number. These are just all these different sets. So you'll see homework questions. How am I doing? Yeah, I thought so. You'll see homework questions that look something like this. Let's see. Squeeze one in over here. All right. Circle all the numbers that are rational numbers, or which ones are rational, or which ones are integers. How about that? Which ones can you make into a positive integer, whole number, or an opposite, an integer? Positives or negatives? Well, 3, that's an integer, right? Well, not kind of boring, but 9, square root of 9 is a 3. So this is also an integer, right? Again, it's not obvious from the way it's written, but it can be simplified to an integer. Which ones of these are rational numbers. Which ones of these can I make look like a fraction? Well, I'm going to start backwards since I put my exception on the end. Here's that repeated decimal, 1.3333. Repeated decimal, yes, it's a rational number. Here's a fraction, obvious, definitely a rational number. Square root of 9, I just said, oh, that could be a fraction, rational number. Decimal that stops, 1.4, it's like 14/10. Yes, rational number. Well, there's my 3 again. So here's my one that was the irrational number. Can't write that like a fraction. You'll see questions like that, ask you to do that. List them, identify them. I can already tell, I kind of like the way this discussion's or presentation's going today, and it means I'm not going to really get to 1.9 today. I can almost guarantee you I'm going to try to adjust our schedule and bump the test to next Tuesday, so we have more time for the rest of the stuff this week. All right, the other things you're going to see, and I want to get out my examples here in this section, is here's a bunch of numbers, put them in order from smallest to largest. And it's kind of like you understand where it would go on the number line, all right? (1.9), which I guess we'll get to tomorrow, talks about properties. You may have heard of like commutative property. You can change your order, or associative, distributive. That's what we're going to talk about tomorrow. But for instance, today, just simply, they'll start with almost backing up a couple sections, put the inequality sign. Which one's bigger? Think of it where it is on the number line. That's a bigger absolute value, but it's further left. It's more negative. So this one's actually the bigger number. All right. Maybe they'll mix in some, how about this? 1.15 or 1.015, which one's bigger? Here's where you kind of have to start on the left and compare place values. As soon as you get to place values that aren't the same, you compare that place value, which one is the larger number? Well, the ones are the same. Even though they're both 1.5, this is really saying 15/1000ths. This one's saying 15/100ths. Those are all bigger pieces. But as soon as I get here, I say, oh, they're not the same. The 1 is bigger than the 0, so this one's the bigger number. Notice I didn't include any negatives. If it was negative or more negative, you'd have to watch out for that. Comparing place values. As long as they're the same, then oops, you found the first one that's different. And you evaluate the relative size there. Okay. Which one's bigger, 2/3 or 7/12? Oh, how do I do that? Get a common denominator in those fractions. So you're looking at the same size pieces. Well, hopefully they won't be too messy. I can turn that into 12ths pretty easily by multiplying by 4. Got to do the equivalent fraction. So this is 8/12ths versus 7/12ths. Oh, okay, now I can tell that one's bigger. Get a common denominator on the fractions. Then you're looking at apples and apples and not different size pieces. And then you get a mix of stuff. Oh, I don't want to get too crazy. Well, put those numbers in order from smallest to largest. Well, like I just said, I got fractions in there, so I'm going to make them all into fractions with the common denominator. Even if one was a decimal, I might rewrite it as a fraction. So now that's really like 4 over 1. 10, 2, 6, and 1. What's going to be the lowest common denominator? Do your multiples, 10, 20, 30, 40, 50, 2, 4, 6, 8, 10, 12, 4, 6, 12, 18. Yeah, I could do 6 times 10 and get to 60. That would work, but how about 30? I'd run into 30. If I make these all 30ths, that will be a common denominator. Well, how do I make that? It's 3 over 3. I'm going to get 9 30ths. How do I turn that into 30? 15, right? 15. That's going to be 7 times 50. 7 times 5 is 35. And 105. 105 30ths. 5 over 5. You get to 55 30ths. And obviously 30 over 30. 120 30ths. Now I can put them in order from smallest to largest. 9, 55, 105, 120. Mom might want commas. Okay. That got us through 1.8. So it's as much as I have time for today, as much as we will cover. I'll expect an updated schedule. All right. I've already kind of worked it out on paper myself a little bit, anticipating this. So we can have a little more relaxed time this week, and we'll come back Monday and review, next Monday and review for a Tuesday test. If, I always start out, see how quickly we can get through the beginning. It gives us more time at the end, but I'll do what's reasonable. All right, questions before we go? All right, good luck, guys, and get that homework done. If you really get stuck, send me your questions, but honestly, with a few things I got to do, it might be middle of the afternoon before I will get back to you, but I will if you send me questions today, especially if you're having scanning trouble or anything like that. All right. Then, all right, I'll let you go, or let me go, and I'll see you guys tomorrow. Okay.
Thanks, Steve.
Okay. Bye. Have a good day.